Thursday.
Thursday.
Last theorem. Divergence theorem. So Green's theorem said what?
If you have an enclosed, if you have an enclosed curve, a 2D enclosed curve in a 2D vector field, well then you got the circulation one and the flux one. The circulation one says that you can find the integral with the difference of, I'm going off the rails here. I can't put it succinctly, I'm sorry.
Circulation of a vector field is the double integral. Partial q, partial x minus partial p, partial y. So it lets us write circulation as a double integral.
Okay.
What was Stokes' theorem?
Circulation as double integral and flux.
Not worded properly.
The double integral and curl.
So I wouldn't word it as a double integral. It's a surface integral.
Okay.
Right, so flux of the curl field. Circulation is flux of the curl field, which is pain. So what do we think divergence theorem is?
Triple integral of the vector field.
What's going to be triple integral?
The vector field.
Let's just write a closed surface integral as a triple integral. So the flux of F through the closed surface S, where S encloses a region W, can be written as the triple integral over W of the divergence of F. Again, important note, positive orientation. So outward pointing normal vectors. The figure uses E to represent the region instead of W, but it's the same thing. Same idea. So again, just like with the previous two theorems, where your path had to be closed, divergence theorem can only be used if your surface is a closed surface. Box is a closed surface. Box without the lid is open. This is the best theorem. There's no more of that garbage flux calculations, as long as it's closed. How do we start Green's theorem and Stokes' theorem? So we first looked at theorems, and then what did we do?
Proved it.
Not proved it.
Verified it.
We verified it. Why change tradition? Very useful theorem for you when you're taking an M.
Will be soon.
Going to verify divergence theorem for that vector field and the region that is bounded by x squared plus y squared equals 4, z equals 0, and z equals 3. What kind of region is that?
Oh. It's a circular cylinder.
Pretty sure that's a
You're missing a word. A right circular
A
cylinder.
right circular cylinder.
What's the axis?
The axis is the z axis. Yes.
What's the height?
The height is 3.
What's the radius?
2.
Why are you freezing so much today? That is the surface we're dealing with. Actually, that's the region we're dealing with. But that region is being enclosed by a closed surface, specifically a cylinder. So let's start with the flux integral. We need to parameterize the surface. Oh, but wait a minute. There's 3 surfaces, aren't there? You have the top, the bottom, and then the side. Start with the top. How do you parameterize the top?
cosine theta, r sine theta, and let's see, would you just say 3?
Because just a circle of radius 2
Yeah,
on the plane z equals 3.
right. Now, I would imagine we're going to do a triple integral with bounds. And we want that to be 3, but not z, even though we want the r to be r and not.
Well, this isn't a triple integral.
Okay.
This is the flux integral we're doing.
Um,
So we're doing surface integrals.
okay. Okay.
R goes from -2 to 2, doesn't it? Oh, yeah, because it's squared.
Oh no, it goes from 0 to 2.
R 0 to 2.
And then theta is from 0 to 2 pi.
Oh, wait, wait.
What's the normal vector?
Zero, zero.
I agree with those two. Zero zero R. That's the top. What about the bottom?
R cosine theta, R sine theta, and then instead of 3, it's a 0. It's the bottom. Has the same bounds of 0 to 2 for R. 0 to 2 pi for theta.
It froze. I have to wait. I don't know why it's freezing today.
It's cold. I know, I'm sorry. I'm sorry. I wasn't thinking. I wasn't thinking.
You should have said that you came up with that.
I spoke without thinking.
Get a double-bladed knife and attach it to one of the ends of my my pointer so I can.
Oh man.
It's okay. 300 points from your final grade.
Yeah, I should have known.
See you next semester in Calc 3.
Yeah. Maybe I could use.
And I'll see you the
practice.
semester after that in Calc 3.
Get a lot of
Because
practice.
it carries over.
Sure.
So that'd be what? You have to take it 4 times?
And maybe then I'll finally be good at it.
So the normal vector for the bottom.
0, 0, minus 1.
Now we need a parameterization for the side.
the side, is the surface, right? Or is
Yeah,
it
the
up?
side of the cylinder.
So it would be 2 cosine theta, 2 sine theta, and then z. Theta goes from 0 to pi, z goes from 0 to 3.
It's a normal vector.
Cos theta, sine theta, z.
The z component's the easy one to figure out here. Has to be perpendicular, right? What's the z direction? So the z has to be 0. No matter where it is, right? Imagine they're spinning around. It's never going to be pointing in the z direction to be perpendicular. So the z component has to be 0. Two cosine theta, 2 sine theta is 0. Make sure they're all pointing in the right direction. Is NT pointing outwards, away from the surface?
Yes.
Yes. Is NB pointing away from the surface? Is MS pointing away from the surface?
Does it matter if it goes through the surface at first, or just that it's going away from
It wouldn't ever actually go through the surface based on how we draw it. So you start it on the actual surface.
Oh, yeah. Okay. Oh, yeah, that makes sense.
So if it's outward pointing, it shouldn't be going through it. If it's inward pointing, then
I was messing up my XOYs. So when you say 0, 0, R starts already off the wall, so then choose off. Yeah, that makes sense.
so does that point away from the surface? It does. So we're good. They're pointing in the right direction. So the closed surface integral doesn't matter the order in which you write it, but it's the sum of the 3 surface integrals. Right, so it's going to be sum of the flux through the bottom, plus sum of the flux through the side, plus sum of the flux through the top. This is going to be a pain. So double integral over the domain of the bottom. Evaluate the bottom parameterization, or I'm sorry, the vector field over the bottom parameterization. What do you get?
Four R cosine theta.
At least I noticed it before.
Minus 8R squared sine squared theta.
Minus 8.
Minus 2.
No, minus 4.
Minus 4.
That should make it square then, so it'd be negative 2R sine, R squared, sine squared, theta. And that's just 9.
0.
We're doing the bottom first. Dotted. You want to freeze again? That'd be nice. With the normal vector. Because of how much it's going to take, I'm going to do each one individually. So let's just say we're calculating the bottom flux first. Oh, well, that's very easy. What's that dot product?
All zeros.
So there's no net flux through the bottom. Let's look at the top. Evaluate the field across the top parameterization. And it shouldn't be difficult.
4R cosine theta. Negative 2R squared sine squared theta. And then that one's not.
Dotted with
0, 0R,
normal vector.
which is left with 9R.
What's that integral?
$36 pi.
How'd you get it?
It would be integral from 0 to 2 pi of 9RdR, and then same thing, but let me restart that. 9R, and the range for R is 0 to 2, range for theta is 0 to 2 pi. So you do that integral.
You did it the hard way. Isn't RDA the polar differential? That's an area integral. 9 times the area of the circle.
Okay. 36 pi.
Circle's radius 2, so it's 4 pi is the area, times 9 is 36 pi. Now for the side. Eight r cosine theta. I'm sorry, not r. There's no r. It's just 8 cosine theta. Negative 8 sine squared. And then z squared. Dotted with our normal vector. Perform that dot product.
16 cosine squared theta minus 16 sine cubed theta.
Oh, look at that. There's no r. So anything with respect to r is just 3, isn't it?
Since you're integrating by interval, I forget the exact words. Those zero.
That's cosine squared, not cosine.
Shouldn't it be dz instead of dr?
It should be dz showing that. Can use the reduction identity on cosine squared. Sine cubed, sine times sine squared. Sine squared is 1 minus cosine squared. That clearly integrates out to 0. That sine theta is going to integrate out to 0. What about sine times cosine squared? That would be a u sub, wouldn't it? What is your u?
Minus cosine squared.
Ignore the 1. I distributed the sine through.
Just minus cosine squared, or you can do sine
So,
Cosine.
yeah, it's just cosine, right? What's the period of cosine? That's going to integrate out to 0. Which means that whole last term integrates out to 0.
So then all you're left with after doing the integral is pi. So that's 48 pi.
So what's 36 plus 48? 84 pi is the flux. Oh, that was only half the problem. Now I have to set up the triple integral. So what we have to do is describe the region that is enclosed by the surface.
Do you mean like parameterize it? Or like describe the bounds?
Describe the region itself. So like we were doing when we did triple integrals.
I don't think I understand. You mean like set up the triple integrals?
Right, because that's what we're doing, right? We're setting up a triple integral.
Yeah. Oh,
So remember we always described the region before setting up the triple integral?
okay, so like cylinder? Right cylinder?
So you want to use cylindrical coordinates?
Yeah.
What does R go from?
0, 2.
What about theta
0 to 2 pi.
and Z?
0, 3.
We also need the divergence. What's that divergence? In cylindrical coordinates. Write the integrand in cylindrical coordinates. What is it?
Four minus 4 r sine theta plus 2z.
What is the differential in cylindrical?
R d theta. RDZ, DRD theta.
Integrate with respect to theta first. What do you get?
For theta plus 4r cosine
Oh, you're doing way too much work.
plus 2.
Roughly, by the way.
Yeah, that's right. That's right.
You're doing way too much.
0. Okay, that's right. It's 2 pi.
And now there's no thetas.
There's no thetas.
So you integrate with respect to theta, you're going to be able to factor out 2 pi.
Yes.
Actually, scratch that. I don't want to streak that R through. Integrate with respect to R now.
Why is it minus 2z now instead of plus 2z?
It's just 2.
It's just 2.
Well, then the whole thing becomes 4 pi integral from 0 to 3 of 4 plus 2z dz. Yeah, it's just like you wrote. Yeah.
Four from 0 to 3 is 12, right?
Yeah.
And it should be plus 16. No. Plus 9. Twelve plus 9
21,
times 4 pi.
84 pi.
Is that what we got when we did the flux integral?
Yeah.
Divergence seems to be verified. Now here it's really obvious. Triple integral is always the best route. Look at the difference in work. That was all just to do the flux integral. And that was a simple surface too, that was just a cylinder. Now we have a cube. many surfaces does a cube have?
6.
Which means you'd have to do 6 surface integrals. Oh, but wait. Cube is a closed surface, isn't it? Describe the region that it encloses. And you can also now think of the surface, S, as the boundary of W. Right, so if you want to use that notation.
X, Y, and Z go from -1 to 1.
What is del dot F?
-2.
So the flux that's a volume integral. So that's -2 times the volume of the region. What is the volume of that cube? There's your outward flux, -16. So much easier. At this point, let's point out that these 3 theorems only work for vector fields, not scalar functions. So if this was, instead of a vector field, if that was a scalar function, f, that you had to find the surface integral of, unfortunately you'd have to do the 6 surfaces. That's why you cry. Let's try and get a picture of this. We got x squared plus y squared equals 4. Z equals 0. And the paraboloid z equals x squared plus y squared. use that view. Maybe something like that. Let's get it here. So the first thing to ask, is this a closed surface? Yes, it is. So we can use divergence theorem here. So describe the region that is enclosed by this surface.
We can describe it using cylindrical.
That's what we want to use.
Thing is still a full circle, so E 0 to 2, 5, and then Z goes from 0 to R.
R squared.
Are we looking at that cup shape inside? Like, I'm trying to, what we just found the bounds for, what does that look like of what we have drawn here?
That is the region.
All right.
That's the entire region being enclosed by the surface.
On the inside of the cylinder, it's between the walls of the cylinder and the walls of the gravel.
Yeah.
Okay. All right, I see. I see.
Right? When you're dealing with a surface, that probably doesn't matter
Right.
on the inside because you just care about the surface.
Right.
But what's the region that's being enclosed?
Right.
I have to include that parabola.
Right.
Or paraboloid.
Yes.
Does that make sense?
Yeah, I think so. So it's like that corner rotated around, that point rotated around the origin, right?
The region is just
Yes.
everything
Right, got it.
inside the orange but outside the green.
Got it. Thank you.
Wait. We need divergence. minus 1.
I was trying to write out the formula, not the whole it.
Yeah, 0's for the first.
Yeah.
So there's how we're going to find the flux. What is the integrand in cylindrical?
R cosine minus 1 for parentheses and all that with the R.
Well, that's not the integrand. That's the integrand right there. Then the differential is what?
DZ, DR, D theta with the R. Yeah.
Let's do two integrals at once. That r squared cosine theta is 0. There's no other thetas. So you can factor out a 2 pi. Oh, there's also not a z. What's the length 0 to r squared?
R squared.
That's what we're left with. So it's going to be negative pi over 2 r to the 4th from 0 to 2. What's 2 to the 4th?
16.
Divided by 2. So our outward flux is a negative 8 pi. This one isn't too terrible to do using the flux integral because it's just a right circular cylinder as the surface. Be the right circular cylinder of radius 2. You then just have to figure out how high does it go. And that's where the paraboloid comes in. And it goes up to 4. And then it's just like the first problem we did. Except instead of a height of 3, it was a height of 4. Replace F with E. Here's an electricity problem.
Oh, yeah, I just talked about this earlier today with somebody. What's his name?
Flux of the E field, I don't know.
It's some sort of, yeah, isn't it?
It's just flux of the E field through a sphere, which is very common. We do a lot of spheres in E&M for some reason. I don't know why. We just do.
I was thinking about boss as well.
Yeah, Gauss is something different.
Yes.
Gauss doesn't deal with flux, I don't believe. Does he?
Gauss is having to do with like I had people relate the surface integral and like with the double.
I think Gauss's law does wind up being flux, yeah. It says flux is equal to something. Flux of the E field equals something in integral form. Differential form is the better one. I love differential forms of Maxwell's equations.
The Maxwell's equations, I was literally talking about those earlier.
Is a sphere a closed surface?
Yes.
Yes, it is. So describe the region that is enclosed by this sphere.
Well, in polar coordinates, or I'm sorry, in spherical coordinates, you would
What are the coordinates in spherical?
have rho, phi, theta, and phi. And rho goes from 0 to a. Theta goes from 0 to 2 pi. And phi goes from 0 to pi.
What's the divergence?
Um,
X squared plus 3y squared plus 3z squared. Which in
oh,
which is 3 rho.
What is the integrand? X squared plus y squared plus z squared in spherical coordinates.
3 rho squared.
rho
What does the differential become?
rho sine squared phi d d rho d phi d theta.
It's rho squared sine phi.
Ah, man. Okay. Right. Of course.
Oh, we don't have a theta. Rho to the fourth, integral from 0 to a.
A to the 5th over 5.
That's not how I want to write it. That's how I want to write it. What is that integral? It's one we've done a lot.
Negative cosine.
That's 1.
Is it like 2?
It's 2.
Uh-oh.
There's the outward flux. So now I could say, okay, here's this vector field. What is the outward flux of this vector field through the sphere of radius 10? And you'd be able to easily do it. (12 times 10 to the 5th over 5 pi). missing from my notes? Oh, yeah, also. Not there. What's missing from my notes, I think, is the plot.
Comment toward one.
We want y plus z equals 4. Or x squared plus y squared equals 16. And it's the first octave. Why did I do z twice? You. More difficult than that might actually be good. So why don't I also now, first off, include the legend. That'd be nice. The 3 planes as well. So the wedge, how would it look if I did viewpoint above? That actually kind of works. Maybe twist it a little bit. So the wedge would be And the bottom. The bottom as well. Just think of picture. Is that a closed surface? Yes, it is. So we can use divergence theorem. We need to describe the region. What coordinate system would be best? Cylindrical?
I would be inclined to stay with rectangular for this.
Rectangular is actually the best here. Because of all those planes.
Right.
X goes from 0 to 2. Let's fix that right now. What's Y going to go from? I'll get you started.
Should go from 0 to root 16 minus 4x squared.
And what about Z?
0 to 4 minus y.
What's the divergence?
Minus X.
Yep, just negative X.
Your choice to fix x as the first step in setting the bounds, did x over y jump out? Should anything jump out at us as being a good, as x being the one to fix for sure, or could we have just as easily fixed y?
Could have fixed Y.
Okay,
Y would go from what?
y would go from 0 to 16.
Uh-huh.
0, 4.
0 to 4. What would x go from?
And then x would go from 0, 16 minus y squared, square root of that. Wait a second, no, divide by 4, then take the square root of that. Okay, so it'd be a little messier,
Why do you think I fixed x?
because it's not as messy, right?
Because y would then involve a fraction.
Right, because then we're dealing with a fraction, yeah.
Or x would involve a fraction otherwise.
Right,
And
That's good.
I don't like fractions.
that's good. If you can avoid them, yeah. If you can avoid them.
That's why I fixed x.
Yeah, so that's good. That makes sense. That's nice. Thank you.
Zero, 2. 0 to root 16 minus x squared. 0 to 4 minus y. Pull the negative out. dz, dy, dx. Has to be that order. Based on how we described it. Oh, z's easy to do. Ultimately, I'm going to have to distribute that x through. Integrate with respect to y. That's your first term.
Minus x times 16, in open parentheses, 16 minus x squared. Four x squared over 2. All of the whole. Okay, yeah. But you're right.
That's going to give us what? 2x cubed. Oh, actually, let's get rid of that negative on the outside now. That becomes negative, this becomes positive. That's what, 8x? Oh, what happened? File cannot be saved, cannot be uploaded. Go away, go away. Go away. Minus 2x cubed. Minus 4x squared is 16 minus 4x squared. Which equals what? 4x squared minus a half x to the fourth minus plus a half times 2/3, 16 minus 4x squared, all to the 3 halves. U sub on that last part. $16 minus 8 plus 1/3 times what is 16 to the 3 halves?
64.
And of course, that's the second term, right? That's lower term, so it's going to be minus that. So 16 minus 8 minus 64/3. Eight minus 64/3 is going to be negative. So there's our outward flux, negative 40/3. Questions on divergence theorem?
More just a comment than anything else. This seems way easier than the previous two theorems.
I agree with Stokes. I disagree with Greens.
The homework wasn't kind.
I agree it's easier than Greens, but I wouldn't say it's way easier.
Seems way easier.
When was Green theorem on the left?
Green was the big three. I was the last two.
I don't remember.
Green's theorem was circulation is equal to the double integral of the partial q partial x minus partial p partial y.
And do you remember what board number it was?
No idea.
Yeah.
It wasn't the last one, it was the one before that.
Yeah, it's two ago.
Let's not say the last one. It wasn't. It was number 21.
There was a specific question I gave him.
So here's how Tuesday's going to work. Bring your laptops in. You're going to have all of Tuesday's class to work on that, as well as ask any questions, last-minute questions before the final exam, which is just exam number 3.
So,
You're gonna be probably